Hi everyone, welcome back. Today we are going to cover another classic system design problem, that is URL shortener. While it seems simple, but underneath there is a fascinating system designed to handle billions of requests with lightning fast speed. And in this video we'll build such system from ground up, and we'll cover the core requirements, estimate traffic, lay out the high level design, and then deep dive into the components that make it all work. So yeah, let's get started. As usual, we'll start with the requirements, which is to understand exactly what we are building. And first up are the functional requirements. And number one being the URL shortening itself, which is that given a long URL, our system must generate a unique, much shorter URL. Given a long URL, generate much shorter unique URL. And next up would be the URL redirection, which is when a user accesses the shortened URL, the system must redirect them to the original URL. Redirect the short URL to original URL. And additionally, we can't just store links forever. They need to expire, and our system can allow users to set an expiration date with shortened URLs. So allow users set an expiration date with short URLs. Okay, so this is what our system does. Now let's move on to the non-functional requirements. And this is all about the quality and performance of our system under pressure, and it is what separates a weekend project from a global production grade service. To start with, a redirection process must be incredibly fast. So redirection should have a low latency. Redirection, and we are aiming for a redirect time of under 100 milliseconds. As this redirection has to feel instantaneous, and any slower, the user experience would suffer. Next up would be the scalability. So what happens when a link we generate for some popular video goes viral and gets hundreds of millions of clicks in an hour? So our system can't just crumble under pressure and should be capable of handling huge traffic without any degradation in performance. Additionally, our service should be highly available. And must be extremely reliable and always online. If the service is down, millions of links across the internet would break. Okay, we know what our system needs to do. Now let's define how our users and their applications will actually talk to it. This is our API design. And it's like the contract that specifies exactly how to make a request and what to expect in return. For a service like this, a simple and a clean REST API is the perfect choice. We really only need two main endpoints. One is for the creating a shortened URL. First, we need a way to create a new short link. For this, we create new resources. The standard is to use an HTTP post request, and the client can hit this endpoint with the post request. Let's call it API v1 shorten. So the client will send us the long URL they want to shorten in the request body, likely as a JSON object, and we can include optional parameters here, like an expiration date. So this will be our request body with long URL and expiration date. This would be optional. So if the request is successful, our service will respond with a 201 status code and will send back the newly created shortened URL. So response will be it will have the shortened URL, and the response header can be the status. The status code, which in case of success would be 201. This is the right path where client sends a long URL and our server sends back the shortened one. Now let's look at the other endpoint, which is redirecting the shortened URL. This is the endpoint that will handle billions of requests. When a user clicks a short link or opens it in the browser, it will make a request to our server. For retrieving or accessing a resource, we use an HTTP GET request, and the shortened code, which is part of the shortened URL, will be our endpoint, and it will be something like some unique characters, which could be like random, something like this, and so our browser would send this request with the complete URL. Let's say this is a domain name, and this would be the request. So now our server doesn't return a web page. Instead, it would perform a redirect. It simply looks up the original URL in the database corresponding to the shortened code and sends back the HTTP response code, which is the redirect response. It will send the redirect response code, which starts with 300 something. So it is supposed to be the redirection code, and the magic is the location header of that response. The browser sees this header and immediately knows that it needs to go to the new URL. So this is the response with location being the URL, original URL or long URL that we sent as part of the generating the shortened URL. And yeah, with this, with just these two simple clean API endpoints, we have a fully functional contract for our URL shortening service. Alright, before we start designing, we need to understand the scale we are dealing with. This is the back of the envelope or napkin math part of the interview, and it's crucial for guiding our technical decisions. So let's start with this. And let's say we can assume our service becomes very popular and has around 100 million daily active users. Now we need to make some reasonable assumptions about how these users behave. Let's say our users, 1 in 10 users create a link, a shortened URL link each day. So with this, like, we'll have around, so 1 in 10 users create short URL. With this, we have the write QPS to so writes per day would be 100 million URL shortening requests per day. And with this, we'll have write QPS to be 100 million divided by, and this number should be roughly around 100 requests per second. And traffic is never usually evenly distributed. It has some peaks. A common rule of thumb is to double the average for the peak. So our peak write traffic would be 200 requests per second. Now this was a write traffic. Now let's take a look at the reads, which is URL redirection part. So assume that a user opens 5 such short URLs within a day. Each user opens 5 URLs per day. With this, we have total request volume to be 500 million requests per day. And with this, our read QPS comes to be million divided by, so this should roughly come out to be 5,000 requests per second. And yeah, we can assume the peak traffic to be twice our normal traffic. So with this, we'll have 10k requests per second. Finally, let's take a look at the storage estimates as well. Assuming that a shortened URL is of 7 characters, with this and we'll be also be storing the long URL, original URL, so which can have a varied length, and we can assume around 500 characters as an average. And additionally, there can be metadata around creating shortened URL, which can be user ID, timestamp, etc. So let's assume it is 100 bytes. So this shortened URL would be 7 bytes, 1 byte per character, and this one would be 500 bytes. So with this, our storage per day would be, we are generating 10 million shortened URLs per day, and each one would take a total of around 600 bytes. So we have around 6 GB of new data per day, and for 5 years this would be into 365 into 5, which is around 11 TB of storage for 5 years. To recap, our system needs to handle around 200 writes per second and a massive peak of 10,000 requests per second, and the total data storage requirements is around 11 TB for 5 years. These numbers prove that we need a solution that is highly scalable, distributed, and optimized for reads. Alright, we have established our requirements and the massive scale we are aiming for. Now let's sketch out the high level architecture. We'll start with the write path, where the part of the system that actually creates a new unique shortened URL. So we'll start with the client. And the client will make a post request containing the original URL, and let's say this request first hits our API gateway or load balancer. Which distributes the traffic to one of our application servers, and for the write path I'll introduce URL shortening service. So the request is routed to one of the identical stateless web servers, and these servers would hold our core application logic. And so this service will generate a short code for the long URL, and we'll come back to how the shortened URL is generated. So after the URL is generated, it will basically store the shortened URL in a database. And yeah, we can use a distributed NoSQL key value store like DynamoDB or Cassandra. The data is structured very simply with the shortened URL code itself as the primary key. So these are URLs DB. Code would be the primary key, and when we write the new record, we can also include the information about expiration time or TTL, and this field will be mapped to the original URL. And TTL or expiry time. So the server simply writes this new row to our database. The TTL approach would be preferable over the expiry time because of its simplicity, and the database itself would handle the cleanup logic. And for the URL generation, shortened URL generation part, there are multiple approaches. The first and the most common approach is to use hashing. So we can use a cryptographic hash function like MD5, and you take the long URL, run it through the hash function, and get a long string of characters. Since we only need about 7 characters, we can truncate this hash, meaning we just take the first 7 characters. So this, let's say, so this would be the algorithm: hash the long URL, and it generates some long string and so on, and we just take the first 7 characters and this would return. So assuming this so this hash function like MD5 generates some 128-bit number, which is converted to a base 64 representation, and then it is truncated to pick only the first 7 characters. So this is the algorithm, but the problem with this is that it could lead to a lot of collisions. So 2 different URLs can happen to produce the same exact short ID with this approach, and in a system with billions of links, this is bound to happen. So this would lead to collisions, and to resolve these collisions, we can append some fixed prefix and retry. So this is fine, but it makes our system's performance unpredictable. This is unpredictable, and for a high performing system, this this wouldn't be optimal. I'll just move this one. And we'll discuss the algorithms here. So we discussed hashing. Another approach is to use a centralized counter or unique ID generator. So with this approach, we use a database or auto-incrementing ID. The first URL would be 1 and the second would be 2, and so on, and we convert that number into our base 62 format. So use database IDs. So let's say we generate like our URL centralized counter generates this as the ID, and will base and 62 encode it to do base 62 encoding, and which will give us G8. So this guarantees uniqueness, but it has some flaws. One is a single centralized counter that every server has to ask for the next number becomes a massive bottleneck. And one is single is a bottleneck. And additionally, our short codes are now very predictable. Users can guess the next short link like after G8, which will be G9, and which is a security and privacy concern. So it is predictable and is a privacy concern. Now this brings us to the one of the perfect solutions for our approach, which is to use a shared pool of pre-computed unique IDs or keys. So instead of generating an ID on the fly, our URL shortening service will pull from a massive shared pool of unique IDs which have been generated ahead of time. So pull from one of the massive pool of unique IDs generated ahead of time. So here's how it will work. So we have a central database table filled with millions of pre-generated random 7-character keys. Background job keeps this table topped up so that it never runs empty. Now you might be thinking, won't all the servers fight over the same keys? You are right, that would be a problem. Grabbing keys one by one could be slow and lead to race conditions. The solution is to use batching, and each instance of our shortening service doesn't need to ask for keys one by one ahead of time. Instead, it would ask the database for a batch of 1,000 keys in a single atomic transaction. It then stores this batch in its own local in-memory cache. So we'll use batching and use atomic transactions to mark the keys which have been consumed, so that no other instance of our URL shortening service gets accesses the already consumed IDs. So here's how the flow would look like. A user requests a new shortened URL. The shortening service checks its local in-memory cache for an available key. If the key is available, it would use one, and it will use fetch, consume and use one. And this is extremely fast because it requires no database call. If the local cache is empty, the server connects to the central database, and it runs a quick transaction to grab another batch of 1,000 unused keys and marks them as claimed. So this with this it loads a new batch into the memory and then proceeds with the step of fetching one ID from this in-memory cache. So this approach gives us the best of all worlds, and vast majority of requests are handled in memory with maximum speed, So we're fast speed and our there's no privacy and security concern as well. As our keys are generated in a random order. So this is the best approach, which provides a highly scalable, reliable design, and we'll use this with our design. So our URL shortening service will fetch the IDs from pre-computed keys value, pre-computed key store. So this was a right path. Now let's trace the read path. What happens when someone clicks that link or opens the shortened URL in the browser? So for this, the client would send a GET request. It comes to the API gateway or load balancer and reaches to one of our services. And for the redirection part, we have this redirection service. Here we are. So upon receiving the request, URL redirection service would just check with our data store, check for the shortened URL code in our database base, and since the shortened URL code is the primary key, the database can fetch the corresponding record in a single fast operation without needing to scan the entire table. And if the database returns a record, the link is valid, our server then gets the long URL and sends the redirect response back to the user's browser. And if the database returns nothing, it means either the key doesn't exist, or it could be the case that because it never existed, or because the link has expired and the TTL has caused the database to automatically delete it. So in this case, the server will simply return a 404 not found error. So we have our high level blueprint. It looks good from a distance, but in a system design, the devil is always in the details. Now it's time to put on our engineering hats and do a deep dive into the critical challenges we need to solve to make the system not just work but also work at a massive scale. Remember our first non-functional requirement? We need our redirects to happen in under 100 milliseconds. Fetching the original URL from database for every redirection request is a major performance bottleneck and introduces a significant delay. Databases, while powerful, have inherent latency due to disk I/O, network overhead, and the time it takes to process the query. Solution to achieve faster latency is with multiple layers of caching. So first of all, instead of going to the database for every request, we can use a global cache and think of it as a high speed lookup table for our entire system. So when a request for a shorten URL comes in, the redirection service first checks with this global cache, which would be a read through LRU cache. If the original URL is found, that is a cache hit, we can immediately send back the redirection response. If the URL isn't there, that is a cache miss, the cache then checks with the database, retrieves the original URL, and before sending the response to the service, it writes that mapping to the cache. This ensures that the next request for the same URL will be a fast cache hit. The approach drastically reduces the load on our database and provides very low latency for popular URLs. It's especially effective because of the 80-20 rule. That is, about 80% of the traffic will likely be for the 20% of our most popular shortened URLs. On top of this global cache, we can the redirection service instances can maintain its own in-memory cache. So let's say each of these services have an in-memory cache. So this is a small local cache living directly on the services server, and when a request comes in, the service checks with its local cache first. If the URL is there, it's an even faster lookup than going to this global cache, and this provides an extra layer of speed. It's perfect for handling multiple requests for the same URL on the same machine within a very short period. While it doesn't solve the problem for new or less popular URLs, it provides a significant performance boost for frequently accessed ones. Now we can also leverage users' browser cache to reduce requests to our service completely. So how it works is when the client sends an HTTP response, when the service sends an HTTP response code, we can use 301 status code So when the browser sees a 301 redirection code, it stands for permanent redirect, and it understands that the mapping will not change, and the browser then caches this redirection for any future clicks on that shortened URL. So with this, it will automatically the browser will automatically redirect to the original URL without ever hitting our service again. So this is the most efficient form of caching, as it eliminates the network traffic completely to our service. However, it should only be used for URLs which are truly permanent and will never change. And if we need the flexibility to change the destination URL, or if we want to analyze the metrics, that is the number of redirection requests for a particular shortened URL, a temporary redirect, which temporary 307 redirect is a better choice, as it tells the browser to check our service again for future requests. So we have made our system incredibly fast. This brings us to our next non-functional requirement, that is scalability. Scalability is all about answering one question: how does our system grow? What happens when we go from tens of thousands of users to 100 million? So how do we handle not just the traffic of today, but the viral spikes of tomorrow without breaking a sweat? So we need to scale two different parts of our system. One is the application layer, and then there's the database layer. So application layer, this is the easier part of the puzzle. Remember that we designed our web servers to be stateless. This is where the decision pays off big time. Because our servers don't store any data, they are all identical clones. To handle more traffic, we simply add more servers to the pool behind a load balancer, and this is called horizontal scaling. If the traffic doubles, we double the number of servers. If it triples, we triple them. Modern cloud platforms can even do this for us automatically with auto scaling groups. This makes our application layer incredibly elastic and resilient to traffic spikes. Now the real challenge is scaling the database layers. So right now we have one giant database. The write traffic of around 200 requests per second is fine, but the problem is that 1100 terabytes of data may not fit on a single machine. The solution to this is to split our database into many smaller pieces and with a process called sharding. Think of it as a library. Instead of one massive room with every book in it, the library has sections, and sharding does the same thing for our data. So we split our data across multiple servers or shards. To decide where a piece of data goes, we use a shard key, and in our case the shortened URL ID is a perfect shard key. So we could shard ID starting from A to M can go to shard 1, and ID starting with N to Z would go to shard 2, and in a similar way we can add more shards, or like even we can rely on the hash value of our shortened URL code to decide the shard on which the new entry should go to. And so when a request comes, our system instantly knows which shard they need to talk to, and this is incredibly efficient because it distributes both the data storage and the traffic, the write traffic across a fleet of database servers. So sharding helps us manage the huge volume of data and distribute the write load. But remember our traffic estimates. Our system is extremely read heavy. We might have around 10,000 reads per second. If we send all of these read requests to the same servers that are handling writes, we still may overwhelm them, and this is where database replication comes in. The idea is simple. For every primary database that handles write, we create multiple identical read-only copies or replicas. So we have this. Replicas. So the writes would go to the primary or master, and when a new URL is created, the write operation would be handled by our primary or master database for that shard, and the data is replicated across different replicas, uh, and this usually happens in milliseconds. So the read requests would, when a user clicks on a short link, that redirect requests are sent to this fleet of read replicas. This completely isolates the read traffic, ensuring that a huge spike in links won't slow down our ability to create new links. Now let's also take a look at our pre-computed key store. So how many keys do we need to store, and how much disk space will that actually take? Let's do the math. Uh, a 7-character key using base 62 gives us 62 to the power 7 keys, which is around 3.5 trillion keys, and the key itself can take 7 characters, that is 7 bytes, and a status flag is used for 1 byte, and additional database overhead for indexing, metadata, etc. Let's assuming it takes around 16 bytes per key, and with this we have 3.5 into 16 bytes. This is around 56 terabytes of storage, and so this is a staggering number. And before we even stored it in a single database, storing the keys might not be used for years is incredibly inefficient and expensive. So the solution to this would be, instead of pre-generating the entire universe of keys, we can use a much smarter approach, that is a dynamic rolling pool. Think of it like a kitchen at a busy restaurant. They don't cook every meal on the menu at the start of the day. Instead, they prep a certain amount of ingredients. When they start running low, the cook preps to get the work to restock. But our key store works the same way with a high water and low watermark system. So we can decide to always have a buffer of, let's say, 1 billion keys. This will be a low water mark. So we'll always ensure that we have 1 billion keys in our database. So this would be a low water mark, and our monitor systems, we can have a cron job or a monitoring system which constantly checks it constantly checks the number of available keys. If the pool of unused keys drops below 1 billion, it automatically triggers the background job to start generating new random unique keys and adding them to this database. So the job runs until the pool is replenished to a high water mark, which is 2 billion keys, and then the job goes to the sleep till the time it is triggered again. This approach gives us the best of both worlds. We always have a massive buffer of keys ready to use, ensuring that a write path is fast, but we only store a tiny fraction of the total possible keys at any given time, and maybe a few terabytes instead of the 56 terabytes, keeping our storage cost manageable and our data efficient. And of course, this pool of 1 to 2 billion keys would still be sharded across multiple database servers for performance and reliability. And that is it for scalability. So our system is now built to handle massive internet scale traffic. But what happens when things inevitably break? A server crashes, a network fails, or an entire data center goes dark. A scalable system that's offline is useless. So this brings us to our next crucial deep dive, that is high availability. This is where we talk about designing our system to be resilient and to continue working even when parts of it fail. So our goal is to have no single point of failure. The core principle of availability is redundancy. It simply means having backups for every critical component. For stateless services or application servers, this is easy. Since they are stateless, they are likely identical clones. We run many more than we need behind a load balancer. If one crashes, the load balancer simply stops sending it traffic and others seamlessly pick up the traffic. And for our stateful services, that is our databases, we've already discussed database replication, and it's the foundation for our availability strategy. And as we established, we have a primary database for writes and several read replicas. If the server hosting our primary database crashes, we don't lose all our data because we have multiple up-to-date copies on the replicas. Redundancy ensures that failure of a single server doesn't bring down the entire system. Having backups isn't enough. Recovery process must be instant. So automated failover is the process that detects when the primary server or master has failed, and it automatically promotes a replica to take its place. And this self-healing mechanism ensures that the system recovers in seconds, often with no human intervention. So we can survive. So we can survive a server crash. But what happens if there is a massive power outage that takes down the entire data center? To achieve truly high availability, we must go a step further with geographic distribution, also known as multi-region deployment. So let's say, so we have two data centers. Let's say this one is US, entire system is US East, and then there is another completely similar setup, which is US West. And instead of running our service in just one location, we deploy a complete independent copy of entire system in multiple geographic locations. And a global load balancer sits in front of everything, directing users' traffic to the nearest healthy region. If the entire US East goes down, the load balancer detects this and automatically redirects all traffic to the US West region, and users might still experience slightly higher latency, but the service still remains online. By combining redundancy at the server level and automated failover to handle crashes, the geographic distribution to survive regional disasters, we can build a highly available system that our users can rely on 24/7. And with that, we have a complete system design for a URL shortener. So what started as a simple problem, that is making a long URL short, ended up with a highly distributed system for internet scale. So we tackled everything from ID generation to database sharding, and from different caching strategies to high availability. I hope you really enjoyed the video, and if you did, please do like the video and subscribe for related content. And If you have any questions or suggestions for the next video, please feel free to leave it in the comments. Thank you for watching the video. I'll see you in next one.